The idea that matter might be composed of tiny, indivisible atoms was explored by ancient philosophers as early as the 5th century BC. However, Aristotle and others popularized the idea that matter is infinitely divisible and that all things are made up of different proportions of only 4 elements: earth, air, fire, and water. You can see why Aristotle believed this. If you take any pure material and try to divide it into smaller and smaller pieces, it always looks the same. Gold is just gold, and it has the same properties whether the sample is 50 grams or 0.01 milligrams. Water seems to be the same way. No matter how small the drop is, the basic properties of water are unchanged. The individual atoms are so small that even the best microscopes cannot detect them. In retrospect, this isn't surprising, because atoms and molecules are really small. A molecule of water is about 5,000 times smaller than the wavelength of visible light that travels inside a microscope. So, in some respects, using relatively huge photons to detect such tiny molecules is a bit like trying to detect the size and shape of an ant using a bulldozer as your only detector. The size mismatch is just prohibitive, so Aristotle's ideas of infinitely divisible matter were believed to be true for more than 2,000 years, until the early 1800s. In 1807, a scientist named John Dalton showed that matter must be made up of tiny, indivisible atoms. The development of this modern atomic theory took 2 important steps. The first was the law of definite proportions. It showed that all pure compounds have exactly the same mass fractions of their constituent elements. Water is always 11.2% hydrogen by mass, no matter how large or how small the sample is. Carbon monoxide and carbon dioxide both consist of carbon and oxygen, but carbon monoxide is always 42.9% carbon, whereas carbon dioxide is always 27.3% carbon by mass. Dalton extended the idea to develop the law of multiple proportions, which states that when atoms of different elements combine into compounds, they always do so in a ratio of small whole numbers. Thus, each water molecule contains exactly 1 oxygen atom and 2 hydrogen atoms, but hydrogen peroxide consists of 2 atoms each. Actually, Dalton would have predicted that hydrogen peroxide was a 1-to-1 combination, and he would have written the formula as HO. We now know that hydrogen peroxide is H2O2, but the general idea was right. Dalton's atomic theory relied on the fact that this law of multiple proportions could only be true if elements and compounds consisted of small groups of microscopic, indivisible atoms. Eventually, scientists learned to make microscopes that did not rely on visible light. This is an image of a gold surface obtained with an atomic force microscope. It shows the blurry images of individual atoms in an ordered crystal lattice. This type of microscopy was not invented until the 1980s, so for nearly 200 years, scientists developed atomic theory without ever directly imaging individual atoms. During those 200 years, several landmark experiments were conducted to deduce the structure of atoms. It turns out that they consist of almost entirely empty space, in which a diffuse cloud of extremely light negatively charged electrons orbits a relatively tiny but heavy nucleus containing positively charged protons and uncharged neutrons. Ernest Rutherford discovered this unusual spatial distribution of charges by scattering positively charged alpha particles from extremely thin sheets of gold foil. He found the vast majority of particles passed directly through the foil, indicating mostly empty space. But a small fraction of particles were strongly repelled by the tiny positively charged nucleus at the center of each atom. In this way, Rutherford was able to disprove the more intuitive plum pudding model of the atom, in which positive and negative charges are uniformly distributed throughout each atom. Interestingly, this meant that the diffuse cloud of electrons determines the size of each atom, because the negatively charged electrons of one atom will be repelled by the negatively charged electrons of all the atoms around it. In fact, this structure means that chemical bonds are formed entirely by interactions of electrons, and the main effect of the nucleus is simply to carry the positive charge that allows bulk materials to be electrically neutral. Two other experiments were crucial for completing this picture of atomic structure. J.J. Thomson determined the mass-to-charge ratio of electrons by deflecting the path of an electron beam in a cathode ray tube. And Robert Millikan conducted a famous oil drop experiment to determine the charge of the electron. From these two experiments, the mass of the electron was determined to be 9.1 times 10 to the minus 31 kilograms. It turns out that electrons are responsible for only a tiny fraction of the mass of an atom. Protons and neutrons each have a mass that is about 1,800 times larger than the mass of the electron. Protons have a charge of +1, which is equal in magnitude but opposite in charge of the electron, which has a charge of -1. Neutrons are uncharged. Therefore, neutral atoms always have exactly the same number of protons and electrons. If some electrons are missing, this creates a positively charged ion or cation. Conversely, if an atom binds extra electrons, it forms a negatively charged ion, or anion. The atomic number of an element is therefore determined by the number of protons contained in its nucleus. However, two different atoms of the same element might have different numbers of neutrons. We then say that the two atoms are different isotopes of the same element. Remember that all of the chemistry is caused by the electrons, so different isotopes of the same element will have nearly identical chemical properties. Hydrogen has 3 common isotopes, which are given special names. Normal hydrogen is protium and has 1 proton, 1 electron, and no neutrons. Deuterium also has 1 electron and 1 proton, but it also has 1 neutron in the nucleus, so it weighs twice as much as protium. And tritium has 2 neutrons and weighs 3 times as much as protium. The atomic mass of an element is the average mass of a single atom when averaged over the natural abundance of the different isotopes. By definition, one atomic mass unit, U, is equal to 1/12 of the mass of a single carbon-12 atom. In SI units, this is 1.66 times 10 to the minus 27 kilograms. The atomic mass of carbon is 12.0107 units, because carbon naturally consists of about 1% carbon-13, as well as a tiny amount of carbon-14, so its atomic mass is slightly more than 12. This distribution of isotopes is common. For example, the atomic mass of lithium is 6.941 atomic mass units, because lithium consists of 7.6% lithium-6, which has 3 neutrons and 3 protons, and 92.4% lithium-7, which has 4 neutrons and 3 protons. Chlorine also has 2 common isotopes, chlorine-35 and chlorine-37, so it has an atomic mass of about 35.5 atomic mass units. Molecular masses are obtained by adding the atomic masses of the constituent atoms. So lithium chloride has a molecular mass that is just the sum of the atomic masses of lithium and chlorine. It took a great deal of courage for John Dalton to publish his atomic theory following 2,000 years of belief in Aristotle's notions of infinitely divisible matter. It took even more faith to develop the theory of atomic structure for the nearly 200 years that atoms remained invisible to being imaged directly. Thanks to the work of many scientists, we now have robust mathematical models of the structure and properties of atoms, and we are rapidly approaching a time when the chemical properties of atoms, compounds, and even materials can be predicted by quantum mechanical calculations with a level of reliability that approaches and sometimes even exceeds our ability to conduct the equivalent experiments.